Hello. Today we're going to have a look at how inverse trigonometric functions can be used in slightly novel ways or combined with the formula that we've been working on throughout our trigonometry chapter. So if I take a right angle triangle here and I wanted to describe the angle A, well, I could say something. One of the things I could say would be that the sine of the angle A would be the opposite over the hypotenuse, would be equal to root 3 all over 2. And rearranging that formula, taking the inverse sine of both sides, I would be able to say that the angle A was equal to sine to the minus 1, or inverse sine, of root 3 over 2. Now this will also be called the arc sine sometimes, but you can also call it an inverse sine. So arc sine or inverse sine of root 3 over 2 is the angle A. So the key insight here is that if you have the inverse sine or cosine or tan of a ratio of sides in a right angle triangle, that is a description of an angle. This is the key thing that we must be comfortable with. We have been using this to find angles since second year, but to actually genuinely think about and spot these things as angles is the key insight you need for this style of question. So if we can get comfortable with the notion that the angle is this inverse trigonometric function, then we can do these questions without any bother. And this type of drawing a model triangle is also going to be very important in this style of question. So let's jump into an example. The angle B is equal to tan to the minus 1 of x. What would cos of B be equal to? Cos of this angle B that is described as inverse tan of x. Well, the thing that we need to immediately recognize is that this should be a ratio. So what ratio is it? Well, if it's x, that means that this is secretly over 1. That's the first job done. We've now written that as a ratio. Now we're going to draw the model triangle that allows us to figure out what's going on with this angle B. So if I draw in any old triangle, doesn't matter so long as the right angle triangle, the sides are not going to be accurate and we don't need to worry about them being accurate. But if I have an angle B here, the tan of my angle will be the opposite over the adjacent. So that's going to be x and 1. So 1 is the adjacent, x is the opposite. Now if I want to know the cos of this angle B, I would need to have the adjacent and the hypotenuse. But I don't know the hypotenuse yet. But I do know that a right angle triangle, the sides in a right angle triangle, are connected by Pythagoras. So I'm going to use Pythagoras to find out what my hypotenuse is equal to. So my hypotenuse squared is equal to x squared plus 1 squared. 1 squared is just 1, so my hypotenuse is going to be equal to the square root of x squared plus 1, taking the square root of both sides. So I now have my hypotenuse, x squared plus 1. So I now have the information I need for getting cos of B. Cos of B is just going to be equal to the adjacent divided by the hypotenuse. The adjacent divided by the hypotenuse. And that is what cos of B is equal to. Now, combining these with some of the formula that we have come across earlier on in the chapter, remembering that this business here, if we have a read of this, cos of 2 inverse sine of 4 over 5, this here we must recognize, even though it looks like a big complicated thing, this is just an angle. I'm going to call it A. So this is just the angle A. So to make this look a little bit more familiar to ourselves, we could say that this is cos of 2A. And immediately we know what we're going to deal with. We're dealing with page 14 in our log tables, and we know what formula we're going to need in order to figure this out. So if I go to my page 14 I see that cos of 2a I can write as cos squared a plus sine squared of a. And this I can now do some work with because I know how to find out information about sine and cosine of my angle here. So I'm going to write out a, my angle, is equal to the inverse sine of 4 over 5. So sine A is just going to be equal to 4 over 5. That one is fairly straightforward. But let's use this to draw a model triangle. Or I'll rearrange it. So sine A, taking sine of both sides, so working backwards from where we would have done here. Sine A would be equal to 4 over 5. So let's draw in our model triangle. If sine A is equal to 4 over 5, let's draw in our triangle. Sine of A, so we have A in this corner here, and we have a right angle. The opposite over the hypotenuse is our sine, so 4 over 5. So we're missing our third side in here, and do we need it? We do, because we want to know what cos of A is. We've already got sine of A. So we have sine of A and we're just going to square it, but we need to find cos of A, so we need to find this third side so we can get our cos of our angle. So we're going to use Pythagoras again. 5 squared is equal to 4 squared plus, I'll call it x. So I end up with 25 is equal to 16 plus x squared. When I work that out, I will get that x is equal to 3. So now I have all the information I need to get sine and cosine of A. So let's get back to that point. I'm going to have the cosine of A is going to be equal to 3 over 5. So I now have sine of A and cosine of A, so I can sub them into my equation. So cos of 2A is going to equal cos squared A is going to be 3 over 5 squared plus sine squared A is going to be 4 over 5 squared is going to be equal to 9 all over 25 plus 16 all over 25. Pardon me, I have made a mistake in my formula here. That should say minus. So if we're looking at our log tables, that should say minus cos squared A minus sine squared A. Cos squared A plus sine squared A would be equal to 1. My apologies. So that should be minus, and this should be a minus. So I subtract them from each other. They're both over 25, so I subtract them from each other, and I get minus 7 all over 25 is equal to my business that I started with. So the key insight is to be able to recognize that if you have arc sine or inverse sine or inverse cosine or inverse tan of a ratio, this is an angle, and we can treat it like a normal angle. Often it's nice to do a substitution, which is effectively what I did here. I said that this was equal to A so that it looked a little bit more familiar to me, and it helped me with drawing my model triangle so I could get my sine and my cosine more directly. But the key thing is that our inverse trig functions are angles, and we can treat them like angles, and we can use formulas for angles when we're trying to solve stuff involving our inverse, sine, cosine, and tan. and that is what we need.